Next, we will try to understand energy levels and energy band diagram. Energy level diagram and energy band diagram. In the previous section itself, I have explained you the relationship between the attraction with the nucleus, the relationship between the electrons and the nucleus with respect to its energy level and its attraction with the nucleus. Okay, so here we will just specify it as graphical representation. That's all. That is what is called as energy level and energy band diagram. But it is very important that you understand this topic so that we can classify the material on the basis of energy band diagram. So that will come in the future videos, but for that we should understand what exactly we mean by energy level diagram and energy band diagram. Until now we are trying to understand one single atom of, say, silicon. Okay, so one single atom has the protons and the neutrons, nucleus, then first orbit, second orbit and third orbit. First orbit has 2 electrons, second orbit has 8 electrons and last orbit has 4 electrons. Okay, so when you draw the energy level diagram, this is what is the diagram. This is nucleus, this is the first orbit, this is the second orbit, this is the third orbit, and the energy associated with the electrons which are present in the first orbit, first, second and third orbit. So energy as you move away from the nucleus, the energy will keep on increasing. Okay, energy will keep on increasing, but the attraction with the nucleus will keep on decreasing. So the electrons which are present in the third orbit has more energy as compared to second and one, but they are less attracted to the nucleus as compared to the second and one. That means electrons present in the second and the first orbit. I hope you have understood. So this is nothing but the graphical representation of energy levels of electrons for one single atom. Okay, now let us suppose if large amount of silicon atoms are brought together. When large amount of silicon atoms are brought together, they form a crystalline structure. Okay, so the crystalline structure. Let us try to understand what is crystalline structure of silicon. Okay, so say this is one single atom of silicon. It has 4 electrons in the outermost orbit. Okay, then suppose there is one more silicon atoms. Again it will have 4 electrons in the outermost orbit. Again there is silicon. It has 4 electrons in the outermost orbit. Okay, so similarly, when large amount of silicon atoms are brought together, what happens is there will be large amount of valence electrons available. Similarly, there will be large amount of electrons present in the second orbit. There will be large amount of electrons present in the first orbit. That means they will not be having a single energy level. If there is small change in the energy level of the electrons present in the first orbit of different silicon atom, then what happens? They will not have one single energy level. Instead of, they have a band of energy level. Okay, that means electron present in the first orbit will not have single energy level when silicon forms a crystalline structure. And they form a crystalline structure when large amount of electrons are brought together. When large amount of silicons are brought together, energy associated with the first energy associated with the electrons in the first orbit will not have one single energy level. They will have a range of energy level, because there may be a small change in the energy level of the electrons present in the first orbit. Similarly, there may be small difference in the energy level of the electrons present in the second orbit. Okay. Similarly, there will be small change in the energy level of the electrons present in the outermost orbit. So therefore, when we bring large amount of silicons together, we don't specify it as one single energy level. We specify it as a range of energy level, and that range of energy level is called as energy band diagram. Okay, so the diagram which I have explained you with respect to one single atom of silicon, that was energy level diagram. And now if you can see with this circuit, when large amount of silicons are brought together, now they are not, the electrons will not have one single energy level. They will have a range of energy level, and that range of energy level is called as energy band diagram. Okay, so now the same thing we will represent energy level. So here this is nucleus. Okay, now the first orbit electrons, these are second orbit electrons, and these are third orbit electrons. These electrons in the first diagram, that is energy level diagram, I have represented that by one single line. That means these two electrons will have same energy, and therefore it is represented by one single line. Similarly, the electrons present in the second orbit, 8 electrons, they will all have the same energy, therefore the single line. And the last electrons present in the valence electrons will have the same energy, and therefore will be represented by the single line, but in case of one single atom of silicon. But when multiple silicon atoms are brought together, they have range of energy at first, second, and the valence orbit. Okay, so this is the energy, and this is energy band diagram. So the electrons present in the outermost orbit, in the third orbit in case of silicon, are called as valence electrons, and the energy associated with the valence electrons is called as valence band. Okay, so this is a very important terminology, because we are going to use this term many times in further explanation of semiconductor device. Valence band. So how you will define valence band? Valence band is the range of energy possessed by the electrons present in the outermost orbit. Okay, so valence band, it is the range of energy possessed by the electrons present in the outermost orbit of an atom, of an semiconductor material. Okay, so valence band is the range of energy possessed by the electrons present in the outermost orbit of an semiconductor material. Okay, so now, as I said, these electrons which are present in the outermost orbit, that is valence band, the electrons present in the valence band are loosely attached to the nucleus, right, but has very high energy as compared to the second and the third, right. So this is the third orbit, this is second orbit, and this is the first orbit. So energy of those valence electrons will be very high as compared to the energy associated with the second orbit and the first orbit, while the attraction with the nucleus will be less as compared to the second orbit electrons and the first orbit electrons. That means when external energy is applied, these electrons present in the valence band will become free. They are free to move anywhere in the material, and these free electrons are going to take part in the process of conduction, and therefore they are called as conduction electrons, right. Of course, the energy, you have to give external energy, right, to move the electrons from valence band to free electrons, right, to make it free electrons, and these free electrons are called as conduction electrons. So you have to give energy to this valence electrons to make it conduction electrons, and they will have a range of energy which is called as conduction band. Okay, so somewhere I will write the definition of conduction band. Conduction band, of course, conduction band means conduction electrons. Okay, so conduction band means the range of energy possessed by free electrons which will take part in the process of conduction. See, when I say conduction means flow of charge, right? Conduction means the material start conducting, means current will start flowing in the circuit. So when they become free electron, जब तक वो न्यूक्लियस से अटैच है वो फ्री इलेक्ट्रॉन्स नहीं है, और फ्री इलेक्ट्रॉन्स नहीं है तो वो मूव नहीं करेंगे मटेरियल में, और मूव नहीं करेंगे तो कंडक्शन होगा क्या, करंट फ्लो होगा क्या सर्किट में, नहीं होगा। लेकिन एक बार वैलेंस इलेक्ट्रॉन से वो डिटैच हो गए, वो फ्री इलेक्ट्रॉन बन गए, उसी को हम लोगों ने बोला कंडक्शन इलेक्ट्रॉन्स। और एक बार वो कंडक्शन इलेक्ट्रॉन्स को बाहर से एनर्जी मिल गई तो दे आर इजीली फ्लोइंग इन द सर्किट, एंड दैट इज व्हेन करंट स्टार्ट्स फ्लोइंग इन द सर्किट। हम बोलेंगे कि वो जो सर्किट है वो कंडक्ट कर रहा है, करंट फ्लो हो रहा है उसमें से, right? So that is what has been mentioned. So the range of energy possessed by free electrons which will take part in the process of conduction. Okay, so that is, these two terminologies are very, very important, because on the basis of this we will classify the material as conductor, semiconductor and insulator. I hope you have understood. Now the next topic is very important, classification of material on the basis of band theory. We have already understood the concept of energy level diagram and energy band diagram. So energy band is the range of energy possessed by electrons in any particular orbit, and if the electrons are present in the outermost orbit they will be called as valence band, and when these electrons are detached they become free electrons, they are called as conduction electrons, and the energy possessed by the electrons which are going to conduct, which are free electrons, is called as conduction band. So we have to classify the material on the basis of band theory. So I will draw three diagrams. While I am drawing, you just have to understand the diagram, and accordingly you have to interpret which is the diagram for conductor or semiconductor or insulator. For that I will give you an hint. See, as I said, some energy will be required to move the electrons from valence band to conduction band. Of course, to move the electrons from the outermost orbit to free electron, right? So that energy is called as forbidden energy gap. Okay, that is called as forbidden energy gap, and with the help of forbidden energy gap we can classify the material as conductor, insulator and semiconductor. Okay, so I will draw three diagrams. You just have to interpret which one of is for conductor, insulator and semiconductor. Okay, so in the first diagram what I am doing is I am drawing this is valence band and this is conduction band. Okay, so this is your conduction band and this one is valence band. Of course this is your nucleus and this is the energy associated with the signal. Okay, so this is the first diagram. Let us name it as A. Then the second diagram, it will be like this. Okay, so this is your conduction band, this is your valence band, this is conduction band, this is valence band, and this is the energy gap. Okay, this is the energy required to move the electrons from valence band to conduction band. Only then they will start conducting. So this is the gap. Okay, we will represent graphically by a gap. This is called as forbidden energy gap. Okay, again this is nucleus and this is the energy associated with the signal. Okay, so let we name the second diagram as B, and in the third diagram again this is your valence band, this is your conduction band, and this is the forbidden energy gap, and this is the energy associated with the signal. So I have drawn three diagrams and of course you must have interpreted the materials on the basis of the diagram, that is the band theory, right? Now see, it is very easy for you to I will give you the values. Of course when I give you the values it becomes more evident that which one of belongs to which material. Okay, but just looking at this graphical diagram you should interpret. Okay, what we said, definition for conductors are material which allow current to flow through it. That means already large amount of free electrons are available. What is free electrons? They are called as conduction electrons, right? And that means large free electrons are already available. So do we need more energy to move the electrons from valence band to conduction band? No, already free electrons are available. So as soon as you apply the power, current will start flowing through the conductor. That means the energy gap between valence band and conduction band should be minimum in case of conductor, because as soon as power is applied, current will start flowing through the conductor. No energy gap. That is first. Second, insulator. Insulator means the material which does not allow current to flow through it. That means large amount of external energy will be required to move the electrons from valence band to conduction band, right? Only when the electrons will move from valence band to conduction band, they will take part in the process of conduction. That means current will flow in the circuit. But in insulator, example wood, plastic or glass, does the current flow through it? No. That means whatever external energy is applied, electrons will not move from valence band to conduction band. if they are not moving from valence band to conduction band, current will not flow through it. That means the energy gap, energy required to move the electrons from valence to conduction band will be very high. So when we represent it by energy gap, so the gap should be more in case of insulator. So we have discussed two. Conductor, gap should be 0. In case of insulator, the gap should be more. And what about semiconductors? As I said, semiconductors at room temperature, they will act as insulators. And when external energy is applied, electrons will move from valence band to conduction band. They will take part in the process of conduction and current will start flowing through the circuit. And when the external energy is applied, they will act as a conductor. Okay, so the energy gap will be there, but it will be small as compared to insulator. So now again, if you see these three diagrams, you can easily now interpret, because I have given you the explanation. Now it becomes easy for you to interpret that the first diagram here, there is no energy gap. Conduction band and valence band overlaps each other. So this is conductor. Okay, so in conductor we say valence band is completely empty, while conduction band is completely filled. Okay, that means electrons, a large amount of electrons are already available in the conduction band. So as soon as you apply power, current will start flowing in the circuit. Now see the second and the third diagram. In the second diagram, now I am specifying the forbidden energy gap. This is 1 electron volt and this is 15 electron volt. So now as I have specified the values, it becomes very easy now for us to understand that with more forbidden energy gap, the material will be insulator, and with less forbidden energy gap, the material will be silicon. So the second diagram is for, sorry, not silicon, that is an example of semiconductor. The material will be, of course, the material is semiconductors, and in semiconductor we say valence band is almost filled, conduction band is almost empty. Okay, so that is the specification with respect to electrons in valence and conduction band for semiconductor. And of course the last one, the energy gap is very high. Whatever be the energy you apply, no current will flow through such material. They will be classified as insulator. Okay, insulator. So in insulator we say valence band is completely filled, लेकिन हम बाहर से कितना भी एनर्जी लगा दो, electrons will not move from valence band to conduction band. This is very large amount of energy which cannot be applied. So no electrons will move from conduction band. So we say conduction band is completely empty, completely empty. So this is classification of material on the basis of band theory. I hope you have understood.